we can see that if the wheel rotates a little bit in the positive direction, that we're going to have a displacement, for example, from here to here on the wheel. Now, if I draw that displacement vector, if I enlarge this part of the picture to give us this part of the picture, here's our wheel, slightly curved, and here's our delta S, and here's our gravitational force vector. Now I added some other lines here for reasons that'll become apparent. Our delta S vector, let me just observe that for a 0.01 radian, which is about 0.6 of a degree change in theta, that's going to be a very small change in position here. And the change in position will be from a point on the circle to another point on the circle. In other words, it'll be a chord of the circle. We're going to approximate this, though, as though the change in position is tangent to the circle. Now, if you draw a vector as small as this one's going to be, and draw it as a chord, and then draw it again as a tangent line, they're going to be so close together that you won't be able to tell the difference. Okay, so for this very small angle, we're going to make the approximation that the displacement, the magnitude of the displacement, is equal to the arc distance from one point to the other as opposed to the straight line distance. Again, for a very small segment of a circle, the distance along the arc and the distance along the length of a straight line from this point to this point are practically the same. So we have our delta S vector, and we have our gravitational force vector, and here is how we project the delta S vector and our gravitational force vector to get delta S parallel, meaning the delta S component parallel to the gravitational force, or along the line of the gravitational force vector. In this case, the work done by gravity is just the gravitational force times the delta S parallel. And the delta S parallel, this is the displacement from here to here. That's in the y direction. That's our delta y. Okay? And actually, when I wrote that down, there's no vector over the delta y, so technically this is correct, but I'm going to put absolute value signs around the delta y and say that F grav is the magnitude of the gravitational force. That's just a positive number. Delta y is the magnitude of your delta y displacement, your delta y vector. That's automatically positive. I'm going to go ahead and put absolute value signs around F grav too, just to indicate that. Now, we know that when we multiply this by this, whether this is a vector or otherwise, and there's some subtleties to the whole vector notation in this situation that we'll revise when we start using the dot product, okay? For the moment, I'm waving my hands over a couple little things here. We know since the delta S in this situation is downward and F grav is downward, that the work done by grav is going to be positive. Okay, so we can certainly do what I've done here. Okay, and we know that if we were over here and the wheel was going up, that the delta S would be positive, the F grav would be negative, and the work would be negative. Okay. This tells us that the work done by gravity is this, and it's positive, since again our displacement in the vertical direction is in the same direction as gravity. And our potential energy change, what we call our potential energy change, is equal and opposite to that. It's equal and opposite to the work done by conservative force, and gravity is a conservative force, so it's going to be, and the only conservative force acting here, so it's going to be equal and opposite to the work done by the gravitational force. Okay, so there's a picture, and now we want to make a little bit of sense out of it and also figure out how to calculate this change in potential energy for this particular situation.